We are discussing the topic of concurrency control in database management systems, and we started with that topic in the last two classes. Now today we shall just quickly review what we have studied till now and then continue with the rest of the topics. Now concurrency, or having a multi-processing or a multi-programming environment, always useful because it enhances the throughput of the system. But there are problems which arise due to this, and the first problem is the problem of inconsistency which arises due to the sharing of data. In a concurrent database management systems, we have got a number of transactions which are currently in the active state. So they are all active, but only one of them may be running at a time on a single processor. On a multiprocessor, more than one of them may be running at a time, but they are in active states. Now being in active states, if they do not share any data, then there is no problem and we can simply schedule them in any fashion, and the final result which will be obtained will be okay. However, if they do share data, we have seen in the last class that it depends on the order in which the scheduling is done. That is, if they are overlapped in partial states of execution and the scheduling is done in such a way that a portion of one transaction executes for some time, then a portion of another transaction executes, and this goes on, then due to data sharing, inconsistency may occur. Now in order to prevent this inconsistency, we have got what are the mechanisms of concurrency control in database management systems. For that, we studied what are called schedules. A schedule, given a set of transactions, a schedule is the exact order in which the statements of various transactions are executed in time. We also discussed the issue of serializability, and we said that if two transactions are potentially concurrent, or a set of transactions are concurrent, then whatever be the result of any serial execution of these transactions is a correct answer. Some overlapping schedules are also correct, provided they maintain the consistency of the database system. Then we went on to see how we can detect whether a schedule is inconsistent and how we can prevent a schedule from being inconsistent. There are several such methods which we shall discuss in due course. We have already discussed two aspects, that of conflict serializability and view serializability. We shall subsequently discuss log-based protocols and time-stamping protocols. A quick review of this is done in the next few minutes. Since we cannot completely analyze all the programs which are going to be executed, or all the transactions, we abstract the transactions by retaining only the read and the write statements of the transactions. And whenever prior to scheduling, we just check what is a possible schedule, and based on that schedule we try to see whether that schedule may become inconsistent or not. The criteria that we have are sufficient in the sense that if a schedule is inconsistent, we will detect it. But if we say a schedule is inconsistent, it need not necessarily be inconsistent. Now what are the mechanisms? The first mechanism is called the technique of conflict serializability. There we introduced the idea of swapping. We said that if we have got more than, if two instructions are there in two different transactions of a schedule S, and they access different data, then they the order in which they are executed may be interchanged without changing the final result. However, if they do share data, then the order can be interchanged only if both of them are read statements. If one is a read and the other is a write, we cannot change the order of execution. Now, by such swapping statements from one schedule, we may reach to another equivalent schedule, and we say that these two schedules are conflict equivalent. And a schedule is said to be conflict serializable if it is equivalent to if it is conflict equivalent to a serializable schedule. Now, in this particular case which we saw yesterday, this read B can be moved right up here and this write B can be moved also up above these two. So, we can have T1 followed by T2, which will be conflict equivalent to this particular schedule. So, this particular schedule is a conflict serializable schedule. It is not conflict serializable to all serial schedules, it may be conflict serializable to any one serial schedule. In this particular case, it is conflict serializable to T1 followed by T2. Let us take this example. Here, this read and write Y may be moved right above without violating this, but this read and write cannot be moved above this, nor can this read and write be moved above this. So, either you cannot move both these above all T1 and get a conflict equivalent schedule, nor can you move all this above this and get a conflict equivalent schedule. So, this schedule is not said to be conflict equivalent to any serial schedule. Our idea of conflict equivalence is that this is a potentially inconsistent schedule and we shall not allow it. But we have seen examples in which if we put in the actual information and if we put in the actual statements, the schedule may still be consistent with the serial schedule. But since we cannot analyze the semantics of a program, we shall be rest assured with whatever we have, and some consistent schedules we will also say that we will not allow, because we are abstracting this information and detecting it quickly. And we said yesterday we were detecting it by forming a dependence graph, and in that dependence graph we have got a node in the dependence graph corresponds to a transaction. If there are 3 or 4 transactions in a particular schedule, there will be that many nodes in the graph. Now, if we cannot swap all statements of T2 above all statements of T1, then we will put an arrow like this saying that T1 must be before T2. There must be there is some statement of T1 which must be executed before T2. Similarly, we may have some statements of T2 must be executed before T1. We cannot conflict serialize it above that. And we may have a graph like this. Now, let us suppose we have a graph like this. In this graph, if there is any cycle, in this particular case there is no cycle, but suppose there is a cycle in the graph, say this one, suppose this edge is there. So, there is a cycle like this, there is also a cycle like this. This means that there is some portion of code of T3 which must be executed before some portion of code of T4, and this says there is some portion of code of T4 which must be executed before some portion of code of T3. That means it cannot be conflict serialized. So, detection of conflict serializability will be if the graph is acyclic, then it is conflict serializable. If the graph has got any one cycle, the conflict is not serializable. Similarly, this is one example which we will say is not serializable, because this cannot be moved above this, nor can it be moved below this by the so it is not that it is not serializable, it is not conflict serializable. But let us put in one more write statement here. and let us have 3 transactions T1, T2 and T3. By our analysis of conflict serializability, this is not conflict serializable, because this write cannot be moved above this, nor this write can be moved below this. But if you analyze the semantics of this program, whatever be the intermediate statements, since this is the final value of x that is written and this does not read any value of x, this write, if it is moved here also, it does not matter, because this one reads x, then these two write x, these whatever these two write will be overwritten. So actually this will be equivalent to read x, write x, this schedule and the previous schedule are equivalent, because they will produce the same output, but they are not conflict serializable according to our definition. In order to take this into account, we introduce the concept of view serializability. And we say two schedules are said S and S dash are said to be view equivalent if for each q, if Ti reads the initial value of q in S, then Ti must in the new schedule S dash also read the initial value of q. For each q, if Ti executes read q in S and that value was produced in a transaction Tj, then in S dash Ti must read the value of q that was produced in Tj. There is a sequence of reading, whoever, if Tj has written and Ti has read in schedule S, then in the new schedule also Ti must read whatever value Tj has written. And for each q, the transaction that performs the final write operation in S must also perform the final write operation in S dash. And we say that it is view serializable if the schedule S is view equivalent to a serial schedule. In this particular case, T1 reads the initial value of x, so T1 reads the initial value of x. There is no other read statement, so the second statement is redundant. T3 writes the final value of s, so that is fine. Similarly here, therefore the effect of this write x is not in any case taken into account in these two statements, and therefore whatever be the output of this, it will be the output of this. Therefore this is view serializable. But the difficulty of view serializability is in its detection. Detection of view serializability is NP complete, and therefore it does not form a very practical situation. Though the graph is only a graph of transactions and a number of parallel transactions may be very few, 4, 5, 6, 7. But if that crosses a certain threshold, the detection of view serializability will be very difficult. It is NP complete, it means that it by default some sort of exhaustive testing is the only known option to test whether it is serializable or not. Having studied these two initial strategies, we shall now study a mechanism called Logbase Protocol, which is a slightly different, which has a slightly different philosophy. This Logbase Protocol is an adaptation of the concept of mutual exclusion using P and V operations or locking operations or its various versions which we have in operating systems. In operating systems, this detection, this sharing is due to sharing of elements in the main memory. The difference here being that this sharing is due to sharing of elements in the secondary memory. So we have got similar mutual exclusion ideas which we shall translate in the database terminology and which is typically peculiar to the database environment. Later on we shall study what are called timestamp based protocols, which is a slightly different form. The log-based protocols are different from the view serializability or the timestamping protocols in a particular sense. Here it is the onus of the system to detect whether the schedule is serializable, whether the schedule is consistent, or whether the schedule has got any other properties. On the other hand, like P&V operators, in log-based protocols, it is the honor of the programmer to write the transaction in such a way so that whatever be a schedule, legally whatever is allowed should be correct. So in log-based protocols, the system does not check anything. The system does only one thing. It provides a set of functions which, if used carefully and properly, will yield what we have are consistent schedules. Now, before we start off with log-based protocols, let us try to understand one thing very clearly. We want concurrency. It is not that we want, when we say it is serializable, it is not saying that we are making it serialized. We want it to run in a concurrent fashion, we just want to ensure that it is consistent. For example, in this example, we don't want to run a serial schedule. That we could do without having any concurrency control mechanism. What we would do? We would say run them sequentially one after another, but that's not what we want. We want to run them concurrently so that the throughput is higher, but we want to ensure that its result is equivalent to a serial schedule so that it does not become inconsistent. Now, due to all these things, what we will have is that we will lose certain amount of concurrency. We will not be able to have all possible consistent concurrent schedules, but we will try to have maximum number of consistent concurrent schedules so that the system remains consistent and data sharing is done in a proper manner. In log-based protocols, the system provides a mechanism of locking data. That is, you can say this data for a certain period of time is my own. A transaction can have complete control over a certain piece of data for a certain amount of time. That is the mechanism of locking. For that, you are provided with operations lock a data item or unlock a data item. During the period in which you have locked the data item to the period in which you have unlocked the data item, no other transaction will be allowed to modify that data item. Now, we have got two types of locks. One is called a shared lock and the other is called an exclusive lock. A shared lock has got the following properties. Anybody who uses a shared lock will have to do it like this. If a transaction Ti has obtained a shared lock or has acquired a shared lock on a data item Q, then Ti can only read Q but not write Q. We shall see what shared lock means. Shared lock means more than one transaction can read that data item simultaneously, but nobody can write that data item. The other is exclusive lock. Here, if you acquire an exclusive lock, that is, if a transaction Ti acquires an exclusive lock on a data item Q, then you can both read and write on that data item. Now, let us see the operators that are provided on locks. After how do you acquire a lock on a variable? You have got two functions, lock SX. Lock SX acquires a shared lock on data item X. Lock XX, it acquires an exclusive lock on data item X, and unlock X releases the lock. Now, what does this locking mean? Suppose I have got a transaction T1 and I say I am not writing down all the statements, but suppose I have got two transactions. One transaction does read P assign P plus 50, write P. Another P read P assign P minus 20 and write P. Suppose these are two transactions. Okay. And if I lock P, now if they can run concurrently and if they run in any arbitrary order, that is first this reads the value of P, then this reads P, then this writes P and then this writes P, it may cause a lot of problems. So what we can do is we can lock the data item P during this whole set of statements, and this one also locks the data item P during this whole set of statements. So what have we done? Let us see. Suppose these two are running concurrently. Now out of these two statements, any one of the statements will be executed first. Now suppose this one is executed first. If this is executed first, then this statement is executed, this statement is executed, and time slot is over. Then time slot comes here. At this point of time, when this tries to do a lock P, it will see that this P is already locked in exclusive mode, which means that somebody has locked it, will read and write on that data, and since this will also read and write on that data, this will not be allowed to read and write on that data. So virtually this transaction will wait at this point. The system may just take this transaction into a suspend state till this lock is released, or the system may busy wait its whole time slot on this statement. When transfer of control comes back here after its time slot is over, or it is sent into suspend state, then maybe this statement will be executed. And if the time slot now again is over, it will come back here and see, it will still wait. After it unlocks this one, only then will this process be allowed to go in. So due to this locking and unlocking mechanism, we are providing a sort of atomicity to the operations on the data item P. That is, the statements of a transaction which affect the data item P are either all going to be executed for a particular transaction before any other transaction touches it. This philosophy is the same as the philosophy of mutual exclusion. So we allow only mutually exclusive access to shared data items. However, Suppose there are two more hypothetical transactions and all four of them can occur simultaneously. Here these two transactions are only reading P, they are not writing anything into P. Therefore, they will acquire shared locks. Now, let us see how execution may take place. Suppose now four transactions are running simultaneously. Suppose in the first instance this transaction T1 executes and it acquires a lock P and it executes this and its time slot is over. Suppose the next time slot goes to T3 and it executes lock SP, then will this transaction be allowed to enter this, will be allowed to read it? No, because this transaction will be doing a read and a write, and whatever it reads, if it does in the middle of this transaction, may be slightly inconsistent. Therefore, if somebody has acquired a lock in exclusive mode, nobody can acquire another lock in shared mode or exclusive mode. So, all of them will have to wait till this fellow unlocks. But let us see another scenario. Suppose the first transaction which starts is this one and it executes read, it has not done display and time slot is over, and now control goes to T2 and T2 tries to acquire an exclusive lock. Will T2 be allowed to acquire this lock? No, because T2 can read and write on this data. Therefore, what he has read and what he has done, both of them may be arbitrary, because you do not really know whether T3 has read the data or not read the data. Therefore, T3 may have read the data or may not have read the data, and T4 may have changed the data. This may lead to a lot of discrepancies in the computation. Therefore, if somebody has acquired a lock in shared mode, nobody can acquire a lock in exclusive mode. But suppose he has acquired the lock in shared mode T3, T3 has done a read P and time slot is over and time comes to T4. Can T4 acquire the lock? Yes, because T3 will read and T4 will read. Since both will read and nobody will write on that data, simultaneously this will be allowed. This is allowed. If we had kept only exclusive locks, we would not have been able to have this sort of concurrency which we will get if we keep shared locks. So, based on this locking protocol, we have got the following lock compatibility function. If somebody has acquired a lock in shared mode, another person can acquire a lock in shared mode, true. But anything else is not allowed. That is, if somebody takes in shared mode, nobody can take in exclusive mode. And if somebody has taken in exclusive mode, then nobody can take either in shared mode or exclusive mode. So, this is what is called the lock compatibility function. But the issues of locking and unlocking are not so simple. We may think that suppose we have got a transaction T1 and we have got a transaction T2 and we have got the following statements. I am purposely leaving some blanks so that we will put in our mind you, the onus is on the programmer to write a correct program. those of you who know in operating systems the readers and the writers problem, if you are aware of what is called the readers and the writers problem, this is the disk variation, this is the database variation of the readers and the writers problem. One transaction T1 reads P, deducts 100, writes back P, read Q, add 100, write Q. The other reads Q and P and displays P plus Q. This is a writing and this just reads. So if we have our standard policy of locking, what would we normally do? Since this one is going to read and write, lock XP, unlock P, lock XQ, unlock Q, and this would do lock SQ, unlock Q, lock SP, unlock P. Normally, whenever we use a data item, before we read it, we lock it, and after we have written it, we unlock it. Now, let us see if this is a correct way of doing things. This means that based on this locking and unlocking principle, whatever will be a schedule will be a correct and a valid schedule. Now, let us see if this is a correct and a valid schedule. Let us start from somewhere. Let this first statement, this one. So, in the first time slot, this goes right up to here, reads this, does this, and then the time slot comes here, and the full of this is executed, and then the control comes back here and the rest is executed. This will be allowed by the locking protocol, because he locks P, unlocks P, and time slot is over. Then he locks Q, reads Q, unlocks Q, locks P, reads P, unlocks P, and displays P plus Q. And then, since this transaction is over, transfer of control comes here and this does this. Now, what can happen? What can happen is that initially P is say 500 and Q is say 1000. Then when this is displayed, what will be displayed as P plus Q? 1400. Which effectively means that if at any time the value of P plus Q, which was supposed to be, you will see that your consistency criteria is P plus Q is equal to 1500. The initial value of P plus Q must be same as this, and this is not a serializable schedule. This is not a conflict serializable schedule, provided the value of P plus Q must be same as it was in the beginning of the transaction. So, if you write out your lock and unlock functions in an arbitrary manner, then you may land up in some severe difficulties. That is, you may get schedules which are not legal, which are not valid, or which are not consistent schedules. In fact, you will get schedules which are not even conflict serializable. So, how do we avoid this? What are the guidelines for writing out locking protocols? So, arbitrary writing of lock and unlock protocols will not help. So, is there any guideline for writing out locking, which are called locking protocols, regarding how to write down your locks and unlocks in a manner so that your concurrency is maintained, that is, you still do have some concurrency and yet you do not land up in inconsistent situations, particularly you have schedules which are at least conflict serializable. We shall study that in the next lecture.